Okay, in this segment, I want to finish up a couple of things with linear circuits before we get into the wonderful world of nonlinear circuits or circuits made with nonlinear elements. I want to finish off our discussion of linear circuits with a discussion of capacitors. We will need to talk about capacitors in some cases in our discussion of transistors, including the MOS transistor, or especially the MOS transistor, and also later on in the course we're going to be talking about dynamics, and capacitors play into dynamics very importantly. So a capacitor is denoted by a symbol that looks sort of like this. There's some voltage across it, V, and some current into the positive terminal, I, and capacitance is denoted by C. Units of capacitance are the farad, and 1 farad is equal to 1 coulomb per volt. So for a linear capacitor, which is of course what we're talking about, Q, the charge, so there's a plus Q on the top plate and a minus Q on the bottom plate. Q is equal to C times V. And I, which is dq dt, is equal to C times dV dt. So C is taken to be a constant in a linear capacitor. For a nonlinear capacitor, you might, for instance, have C as a function of V, or something like that. And so then, to take the time derivative, you would actually have to take the derivative of a product. But for a linear capacitor, C is just constant, independent of the voltage across it, and then that's just a constant with respect to differentiation with respect to t, and so I is just equal to C dV dt. Okay. Technically, this is the symbol for a nonpolar capacitor. There is such a thing as a polarized capacitor, and the symbol for that is usually something like this. This is a non-polarized, or this is a polarized capacitor, sorry. And this is the positive plate. And the idea of polarized capacitor is that you have to, for the DC voltage across it, you have to respect the polarity of the capacitor, otherwise bad things happen, like the capacitor explodes and spews hot electrolyte all over your face or something like that, which is a bad thing. There are definitely nonpolar capacitors like ceramic capacitors, and polarized capacitors like electrolytic capacitors. Typically the nonpolar capacitors are available in smaller range of values, and the polarized capacitors are available in the larger range of values, and the crossover is typically in the range of tens of microfarads or so. Certainly when we're working with integrated circuits and designing capacitors on chip, the capacitors are pretty much always nonpolar capacitors where the polarity doesn't really matter. But anyway, so we're going to be considering capacitors in, well, I guess I should say, obviously, it doesn't make much sense to talk about the IV plot of capacitors, since it's a relationship between I and the time derivative of the voltage. You could certainly have a QV plot of for a capacitor, and then it would just be a straight line with a slope of C that goes through 0 at 0. But typically we don't think about an IV characteristic of a capacitor per se. But this is sort of the IV relationship or governing equation, if you like. Okay. So we want to talk about capacitors in series and parallel. So let's talk about capacitors in series first. So we're going to consider, just like we did for the resistor, we're going to put two capacitors in series with each other. With some voltage across the two and some current flowing in. So this is Vn, this is In, this is C1 and C2, and I1 and I2. Well, what do we know about this situation? Well, we know from Kirchhoff's current law applied at the top node that In equals I1, and from KCL applied at this middle node here between the two capacitors, we know that I1 is equal to I2. And so it tells us that basically the currents are the same. KVL applied around this one loop in the circuit will tell us that Vn is equal to the sum of V1 plus V2. And of course we also know from the IV relationship for the capacitor that for each capacitor we know that I1 is equal to C1 dV1 dt, and I2 likewise is equal to C2 times dV2 dt. Okay, so what do we do with this? You remember for resistors what we were doing was we were basically looking to find out the relationship between In and Vn. Okay? Well, one thing we can do is we can recognize that because of the Kirchhoff's current law equation, this is equal to In, and this is also equal to In. Okay? So if we call this equation 1, equation 2, and equation 3, let's say, we can take the time derivative of equation 1. So equation 1 tells us Vn is equal to V1 plus V2. That means that dVn dt is equal to dV1 dt plus dV2 dt. Right? So if you take the derivative of a sum, that's equal to the sum of the derivatives. Okay? Well, we can solve equation 2 for dV1 dt, and that's equal to In over C1. And similarly, equation 3 implies that dV2 dt equals In over C2. If we call this 3 and 4, we can of course substitute 3 and 4 into equation, into the time derivative. Let's call this, I guess we're up to 4, so this is 4, 5, and 6. So 5 and 6 substituted into 4 tells us that dVn dt is equal to In over C1 plus In over C2. Well, we can factor out the common In times 1 over C1 plus 1 over C2, and we can solve for In. Right? So In equals 1 over C1 plus 1 over C2 to the minus 1 times dVn dt. Well, what is this thing? Well, this thing is 1 over the sum of the reciprocals of two capacitances. So this is really C1 parallel C2 with our definition of the parallel operator. So it has units of capacitance, and it's an equivalent capacitance. So, and moreover, this equation relating IN and VN is just the governing equation for the current voltage behavior of a capacitor. So what we've shown here is that two capacitors connected in series behave as a single capacitor whose value is basically the parallel combination of the two capacitances. So capacitors in series combined with a parallel operator. Okay, so just making that picture, what we've shown here is that two capacitors in series, C1 and C2, is equivalent to a single capacitor, CEQ, whose value is given by C1 parallel C2. And of course, if we had three capacitors in series, we could group two of them together and use this equivalence to collapse them into a single equivalent. And then we'd have, again, two capacitors in series, one in the equivalent of the other two, and we could apply that same transformation again, and we would wind up with the idea that three capacitors in series is the triple parallel combination of the three capacitances, and so on. You could then inductively show that n capacitors in series combine with an n-way parallel operator. Okay, so that's capacitors in series. Let's think about capacitors in parallel. So it's the same game. We've got a voltage source here, let's say, that's applying a voltage to two capacitors that are connected now in parallel with each other. And again, we want to find a relationship between IN and VN. Well, what do we know? Well, in this case, KCL tells us that IN is equal to the sum of I1 plus I2. KVL, if we apply KVL around this first loop here on the left, we get VN is equal to V1. If we apply KVL around the second loop here on the right, we get V1 is equal to V2. So KVL tells us that Vn is equal to V1 is equal to V2. And of course we know that the IV relationship, the capacitance for each capacitor, implies that I1 is equal to C1 dV1 dt, and I2 is equal to C2 times dV2 dt. Well, we can substitute in this KVL and write this as C1 times dV in dt, and this as C2 times dV in dt, because V1 and V2 respectively are equal to Vn. And so we can say, well, this is equation 1, equation 2, and equation 3. We can substitute 2 and 3 into our KCL equation to find that IN is equal to C1 dVn dt plus C2 times dVn dt. And of course we can factor out a common dVn dt. And so again we have something which is equivalent to the governing equation for a single capacitor. whose equivalent capacitance is just the sum of the two capacitances that we've connected in parallel. And so just drawing that out, we've shown basically that two capacitances in parallel are equivalent to a single capacitor whose value is C1 plus C2. So capacitors connected in parallel add with each other in the same way that resistors in series do. So capacitors, in some sense, the capacitance is sort of more like conductance than it is like resistance. Right? That's what we're finding out with these equivalences. Okay, so capacitors connected in series combined with a parallel operator, actually like conductances in series combined with a parallel operator. Can't remember if we actually explicitly said that or not, but that turns out to be true. Conductances connected in parallel add just with a summation if you think about their conductance. So capacitance is sort of analogous to conductance in the way that these elements combine with each other in making equivalent circuits. Okay, so I want to consider one capacitive circuit which will be useful in a number of different contexts. Okay, that's a capacitive linear combiner. And then we're going to specialize that into a capacitive voltage divider. Okay, so we're going to consider a two-way capacitive linear combiner for just the simplicity of the situation here. You can obviously generalize this to an n-way. But here we have, let's say, two voltage sources that are inputs. Here we have, say, C1, EN1, and we have here EN2. Connected through C2 to a common output node. So this is our output V out. And there's going to be, say, an I1 and an I2. The C2 here. And there's a plus minus V1 plus minus V2. And we'd like to know how does V out relate to Vn1 and Vn2, which are presumably all functions of time. Okay? Well, what do we know about this situation? Well, we know that the IV relationship of the capacitors imply that I1 is equal to C1 times dV1 dt, and I2 is equal to C2 times dV2 dt. But V1 is really V in 1 minus V out by Kirchhoff's voltage law, and V in 2, or rather V2 is V in 2 minus V out. And so this is equal to C1 times d by dt of V in 1 minus V out. And this is C2 times d by dt of V in 2 minus V out. Now, of course, we can push this derivative through this difference here and write this as C1 times dV in 1 dt minus C1 times dV out dt. And this one we can write as C2 times dV in 2 dt minus C2 times dV out dt. Okay? And we also know from Kirchhoff's current law that in this case, the way that we've written these arrows here, both currents are flowing in to node V out. So I1 plus I2 is equal to 0 amps. Or I1 is equal to minus I2 if you prefer. So what we're going to do is substitute in, so if this is equation 1, equation 2, equation 3, if we substitute 1 and 2 into the KCL, that's going to tell us that get C1 dVn1 dt minus C out, or rather C1 dV out dt plus C2 dVn2 dt minus C2 dV out dt equals 0 amps. We're going to collect the dV out terms, dV out dt terms onto one side of the equation, and then we're going to leave the dV in terms on the other side, and we're going to put the out terms on the left-hand side, so we're going to solve for V out. That's what we're interested in here. So collecting the dV out dt terms onto one side of the equation and flipping the equation around, we would have that C1 plus C2 times dV out dt is equal to C1 times dV in 1 dt plus C2 times dV in 2 dt. Okay? And of course we can solve for dV out dt simply by dividing by C1 plus C2. So dV out dt is equal to C1 over C1 plus C2 times dV in 1 dt plus C2 over C1 plus C2 times dV in 2 dt. Now we can actually solve this equation for V out by multiplying both sides by dt and integrating both sides from, let's say, t equals 0 to t equals t. So doing that, we have the integral from 0 to t of dV out dt is equal to C1 over C1 plus C2 times the integral from 0 to t of dV in 1 dt plus C2 over C1 plus C2 times the integral from 0 to t of dV in 2 dt times dt. Okay? And it turns out these integrals are actually quite easy to do because we can change variables in this integral to V out. We can change variables on this integral to V in, and we can change variables on this integral to, V in 1, and we can change variables on this integral to dV in 2, or rather V in 2. And so this becomes, doing that, this becomes the integral from V out of 0 to V out of t of dV out. And that's equal to C1 over C1 plus C2 times the integral from V in 1 of 0 to V in 1 of t of dV in 1 plus C2 over C1 plus C2 times the integral from 0 to, V in 2 to V in 2 of t of dV in 2. And of course the integral of dV out is V out, the integral of dV in 1 is V in 1, and the integral of dV in 2 is just V in 2. And so what that tells us is that we evaluate V out from V out of t to V out of 0, we get V out of t minus V out at t equals 0 is equal to C1 over C1 plus C2 times Vn1 of t minus Vn1 of 0 plus C2 over C1 plus C2 times Vn2 of t minus Vn2 of 0. So in this particular case, we need to know what Vn and Vout are at some instant in time. That would be like an initial condition. And that tells us that if we then know some value, the value of Vn at some later time, t, Vn1 and Vn2, we can say what the value of Vout is by this weighted summation. Okay. So just like the resistive linear combiner has some weights or coefficients, right? So does the capacitive linear combiner. Each weight is proportional to the capacitance through which it couples into the output, or through which its input couples into the output, and it's normalized by the total capacitance. And these weights are very, very similar. If you go back and look at the resistive linear combiner expressed in terms of the conductances, the weights are the same as they are here with the capacitors. Again, because capacitance is very analogous to conductance. The difference here is that, if you like, the initial conditions are independent on the three things here. So it's really just the change that is let through by the capacitor, which you might imagine, given that the d by dt of a constant is nothing, is 0, and so dc does not go through capacitors, at least not usually. Anyway, so that's the capacitive linear combiner, and the specialization of this, which I wanted to just tack on as sort of a corollary, would be a capacitive voltage divider, a two-way capacitive voltage divider. And so in that case, we really have a situation where, say we have Vn C2, C1. And this is like having, it's like the capacitive linear combiner with Vn2 just replaced by a short circuit. This is a two-way capacitive voltage divider. So this is capacitive, same as and so we can take the result and write that V out of t minus V out of 0 is going to be equal to C1 over C1 plus C2 times Vn of t minus Vn of 0. So the change in the output voltage is going to be the same as the change in the input voltage times this parameter here, which is the so-called capacitive voltage divider ratio. And you'll notice here that instead of being like R2 over R1 plus R2, it's actually C1 over C1 plus C2. And we can relate this to the concept of complex impedance, which you may recall from ISIM. So the impedance of a capacitor, Z sub C, is 1 over j omega C. Okay, so it's inversely related to the capacitance. And so if we think of this as in terms of impedances, the impedance divider here, the voltage divider in terms of the impedances, would be Z2 over Z1 plus Z2, where Z2 is 1 over j omega C2 over 1 over j omega C1 plus 1 over j omega C2. And if we multiply through by j omega over j omega, that gets rid of the j omegas everywhere. And so that's 1 over C2 over 1 over C1 plus 1 over C2. If we multiply by C1, C2 over C1, C2, of course the C2's cancel up here, and we're left with C1. And downstairs here, the C1's cancel in the first term, the C2's cancel in the second term, and so that would be, if we just rewrite that, it's about C2 plus C1, but addition is commutative. And so that's how the impedance divider, or the voltage divider expressed in terms of complex impedances, relates to our capacitive voltage divider ratio here that we've just derived, without the help of the impedance concept. Okay, so that's a special case that we will see come up, especially in our discussion of MOSFETs. But I wanted to just do that before we talk about what we do with nonlinear circuits in the next segment. So we'll see you next time.